Hello, my name is Frank Harris, and welcome to my discussion of Earth's cloud coverage and its role in warming and cooling the atmosphere. I hope you will enjoy this shallow look into a very deep field. Averaged over time and area, a bit over half of the Earth is covered by thick clouds. By thick, I mean that they are optically thick enough to have a substantial impact on Earth's radiative budget. It can be complicated to work out these effects as they are both warming and cooling. As we will discuss, they include shortwave and longwave reflection, as well as thermal emission. This contrast means that there is great uncertainty when trying to quantify their net effect. In this talk, I will start with an explanation of the complex physical processes involved in cloud formation and their existence. Next, I will provide a brief overview of remote sensing as it relates to clouds, discuss pertinent concepts, the main challenges involved, and go over some of the instruments in use. Finally, I'll take a look at the net effect of clouds on the Earth's climate and try to impress on you the uncertainty in this value. Let's begin with a broad overview of the physical processes going on within clouds. There are important processes over a cloud's lifespan at all length scales, from the synoptic scale to the microscale. A parcel of warm, moist air at the surface is subject to some lifting force. It is adiabatically cooled by expansion as the surrounding pressure drops. As the parcel cools, it can hold less water vapor, and the relative humidity increases. When the parcel is saturated, the water condenses into droplets and cloud formation begins. This process releases latent heat as a result of phase change. This heat can further drive convection and cloud growth. If these droplets are allowed to coalesce into larger drops, their surface area will grow more slowly than their mass. Gravity will overcome buoyancy, and the cloud will precipitate. There are two broad categories of liquid clouds, although there are many clouds that combine the properties of both. The first are cumulus clouds, which are identified by their vertical structure. They're produced by strong upward convection, which allows vapor to condense more aggressively. The release of latent heat drives cloud growth upwards and increases convection. As a result, the air grows drier with height, and available heat is reduced. If it makes it high enough, it will reach the tropopause, where there is no more available water. Convection generally does not continue above this height, so the cloud structure flattens. This abrupt flattening is the cause of the distinctive anvil shape in mature storm clouds. However, if the lifting force is non-convective, such as when the warm, moist air is lifted laterally over a cold front, the results are stratus clouds. These are wide, flat, pancake clouds. Without convection, the most common form of these clouds remains lower in the atmosphere, about 1 to 2 kilometers, but it can also exist at all latitudes. The lack of convection provides fewer opportunities for the droplets to coalesce into precipitation, so they remain longer. Aerosols are also necessary for cloud growth, serving as nucleation sites, known as CCNs. Aerosols can affect cloud size, lifespan, and albedo. There are several effects from the interaction between clouds and aerosols, but generally they stem from the same concept. The greater the concentration of CCNs, the more numerous the cloud droplets. That is, for a fixed amount of liquid water available, the greater the CCNs, the smaller the average droplet size. I'll focus on two of these aerosol indirect effects. The first is the Tuomi effect. More droplets means that the mean free path for an incident photon is much shorter. There are more scattering opportunities, and as anyone who's seen a rainbow knows, water droplets are primarily backscatterers in the visible range. The smaller the droplet size, the greater the optical thickness, and the greater the shortwave albedo. Next, the Albrecht effect comes around from the fact that smaller droplets are going to have a harder time coalescing into larger droplets. This means that the cloud lifetime is increased, and so is the overall planetary average of cloud cover. So this effect does not change the instantaneous properties of the cloud, but the average albedo of Earth increases. A cloud has three roles in influencing Earth's energy budget. First is the cloud's shortwave albedo. This can be as low as 0.25 or as high as 0.7. For cirrus clouds, the albedo can be nearly zero. Again, this variation is due mainly to water droplet size. For bright clouds, this is the dominant forcing term. Altitude has an effect as well, as it is most pronounced for lower level cloud coverage. Clouds are also reflective in the long wave, which has the opposite effect. Upwelling infrared radiation is reflected downwards to be reabsorbed and re-emitted by the atmosphere and surface. As with shortwave, the extent of this is impacted by the droplet size distribution, the thickness of the cloud, and its height. This time, the higher the cloud, the greater the effect, because it covers a larger volume of atmosphere, so there is more path radiation. Cirrus clouds do double damage as they reflect long-wave radiation better than short-wave. Finally, clouds function as gray bodies. Typical temperatures range from -25 to 0 Celsius. If the cloud was a perfect black body, that would mean they would have an irradiance of 70 to 100 watts per square meter. In reality, their emissivity can be quite low, so this value may be substantially lower, again depending on the optical properties of the cloud. Next, I'd like to discuss three significant instruments in the Earth Observing System, or EOS. One of the most widely used instruments is the Moderate Resolution Imaging Spectroradiometer, or MODIS. The EOS uses two MODIS instruments, one on the Terra satellite and one on Aqua, which is in the A train. MODIS cross-scans across a 2,300 kilometer swath, with data resolutions from 250 to 1,000 meters. It features 36 spectral bands, 19 in the V-near spectrum and 17 in the infrared. The table on the right lists the most commonly used spectral bands for cloud study. AquaMODIS was launched in 2002 and its products are still widely used, 17 years into its 6-year mission. On the left is a MODIS measurement of mean cloud top temperature. It appears that the warm regions are not cloudy, and this product has not had a cloud mask applied. On the right is a retrieval of the average effective particle size for liquid water and ice. The large yellow region in the middle shows a mean droplet radius of 9 microns. The main instrument on the Calypso spacecraft is the Calliope LiDAR. See their full names below. It has an unpolarized infrared channel and receives visible light broken into parallel and perpendicular polarized components. Calypso was launched in 2006 and is still active, although the satellite has been moved into a lower orbit, and Calliope has recently suffered from low-energy laser pulses affecting data quality. LiDAR instruments can construct a three-dimensional image of the surface below by timing the backscattered laser light with the pulses sent out to calculate distance. This allows scientists to make retrievals of cloud thickness and internal vertical cloud structure. Droplet count and size distribution can be found as well. A vertical feature mask is also produced from Calliope data so that observations can be categorized into surface, cloud, aerosol, and so on. This is a measurement of total attenuated backscatter. It is the fraction of light the receiver picks up relative to the pulse emitted. A separate product corrects for atmospheric attenuation. And here is the same image, but it shows only the perpendicular component of the backscattered light. Notice the higher features at 15 kilometers are much more strongly polarized than the lower features at 5 kilometers. Finally, here is the vertical feature mask. You can see now that the polarized features are recognized as clouds in orange, and the strongly polarized features are recognized as aerosols in light blue. Clouds in the Earth's Radiant Energy System, or CERES, is a low-resolution, wide-field instrument. The instrument has a 10-kilometer footprint, but a fully hemispherical field of regard. CERES has 3 channels: short-wave measure of reflectance flux, long-wave measurement of emission flux, and a window channel for ground measurement. There are 2 pairs of identical CERES flight models installed on both the Aqua and Terra spacecraft. Why 2? Because of the instrument's dual scanning patterns. The first is a cross-track scan over a wide field of view, such that full daily coverage of the Earth is achieved. The second is a biaxial scanning mode, in which it can scan independently across the whole atmosphere. While its resolution is smaller than other instruments, with its wide field of view and multiple scanning modalities, CERES can generate a full daily measurement of Earth's total TOA flux. In addition to flux, cloud properties such as emissivity, cloud area fraction, optical depth, and droplet size distribution can be calculated. This image shows the retrieval of total cloud coverage percentage over South America in June 2016. Notice the circled region in the lower left, which is nearly full cloud coverage. We'll be looking at the same region in different data products. Here is albedo observation. The same area is seen to have a much higher albedo than any other region in the image, about 0.7. While there was a lot of area with full coverage, the properties of this particular cloud are clearly more reflective. However, the contrast between the South Atlantic and Amazon rainforest with the less reflective clouds is still quite strong. Here's the TOA shortwave flux. Not much difference in clouds in this product. Finally, the TOA longwave flux shows this area being noticeably darker than others in the infrared. This tells me that the cloud is substantially colder and higher than the other clouds. Before cloud parameters can be retrieved, it must be determined whether an observation is a cloud. This is quite complicated, as it can be difficult to distinguish clouds from desert or ice by spectral response alone. We will barely be scratching the surface here. One technique, an algorithm developed by JISC company Sentinel Hub. First, assign a probability to each pixel based on its spectrum. Next, that probability undergoes convolution and thresholding to produce a binary yes-no cloud mask. These problems mean that cloud identification algorithms suffer from great uncertainty. For instance, the most recent algorithm to produce the series cloud mask addresses several of these concerns. These results were validated with the Calypso vertical feature mask, and they were found to be only 80% in agreement at best. As an example, here is a gridded image of multiple Modis true color tiles. And here is its cloud mask. Similar products exist for most instruments. All this attempts to get at the big question. By how many watts per square meter does our cloud system change the Earth's TOA flux? Unfortunately, this question seems largely unanswered. A different question, which has been answered in the context of the bigger picture of climatology, is how anthropogenic factors affect our cloud system, and how that affects the radiative budget. But even this has error bars that are larger than the expected amount. The 2013 IPCC report shows that the aerosol indirect effects we discussed, or at least the portion of the aerosol picture we can blame humans for, is on average about minus half a watt per meter squared, but it could really range from minus 1.5 to 0. Unfortunately, the radiative forcing of clouds is one of the most variable and uncertain contributions to climate. Firstly, it is more subject to seasonal and acyclic daily variation than all other effects. Cloud cover varies in a given region from day to day, and is subject to aerosol and water vapor availability, wind speed, surface temperature, lapse rate, and pressure. These affect the height, temperature, and geometrical optical thickness of the clouds, which in turn determines whether a cloud will have a net positive or negative forcing term. Even supposing coverage were constant and homogeneous, there still exists great variance depending on the attributes of a particular cloud. And of course, there are the aforementioned difficulties in the measurements themselves. These factors combine to make it difficult to quantify the net effect of clouds on TOA flux. The current state of cloud measurement is nowhere near where we'd like it to be, even though it is far better than it used to be. Ceres' wide coverage, in particular, creates a more complete and comprehensive cloud record than we have had before. Also, Calliope's polarized LiDAR gives us a new ability to measure the vertical structure of clouds and reduce uncertainty in cloud categorization. The field would continue to benefit from further research into instrument development, data processing, and modeling. Improvements to cloud identification algorithms in particular would help our uncertainty with calculating cloud coverage amounts and estimating better global flux. Novel near-future instruments may provide deeper insights, but there's also something to be said for staying the course. We are producing truly massive amounts of remote sensing data, and our complete dataset gets larger every day. If you are interested in future development in cloud science research, I encourage you to look at the Plankton, Aerosol, Cloud, and Ocean Ecosystem, or PACE spacecraft, scheduled to launch in 2022.